All right, hi everyone. I'm Jacob Strong from Laurentian University. I'm a research associate with Merck, and I'm currently mapping the Northwest Superior Province using radiogenic isotope systematics. I appreciate the opportunity to complete this work. It's a continuation of my PhD work, and it's funded by the Canadian government's Canada First Research Excellence Fund. However, I also thank all the partners who have provided the necessary support to achieve the wider Metal Earth goals. So first I'll provide a brief update on my publication on isotope mapping progress, then I'll describe some broad similarities between Archean granite-greenstone terranes and a Proterozoic analog, and last I'll describe the geodynamic implications of these broad similarities and provide an overview of peel-back tectonics. So here are my publications from 2023, one in Precambrian Research, another in Lithos, and one presentation at the GACMAC in Sudbury. And these are the three main articles I'm concentrating on this year. The first one's been under review for the past month and a half. I'm waiting on the reviews. I also have two presentations at the GACMAC in Brandon this year, partly because I'm an invited speaker for a special session by the CJS, along with several others. So here are some photos from the 2023 field season showing the pilot, my field assistant, and me. It's always a good idea to check the forecast. Zircon isotope mapping of the Western Superior Province has been progressing, but I don't have any data to show off today because we're just getting ready to start running the samples. My samples are in large purple dots. The map also shows the distribution of previously analyzed igneous rocks, volcanic rocks, I should say intrusive rocks, volcanic rocks, and sedimentary rocks. And relatively speaking, I have a pretty decent spatial distribution in the North Caribou terrain. And I'll also be collecting a few samples which are left over from the Jack Satterley lab to complete the Uchi domain. So in addition to the sample suite from the North Caribou terrain, I can also use the published whole rock samarium neodymium and zircon lutetium hafnium results. I'm able to recalculate the neodymium isotope data and convert it to epsilon hafnium using the terrestrial array. So what this means is that the Winnipeg River, Wabigoon, and Marmion terrains are tentatively complete. And, but I couldn't contour the data for you because I didn't have the right license just yet. So we'll get that fixed when we get back to Laurentian. So, however, despite the addition of approximately 250 data points, this still leaves a fairly significant hole in the region near the Ring of Fire. And so although the cost may be fairly significant, the cost has to be weighed against having a lack of spatial constraints in the general area of the Ring of Fire, which might be kind of important. So all right, so the rest of the presentation is going to focus on the first Middle Earth core objective and explore some current developments in Archean geodynamics that you may or may not be aware of. So granite-greenstone terranes are the primary record of Archean crustal growth, but evidence of formation processes or prevailing geodynamic settings remain equivocal. Archean granite-greenstone terranes are controversial geologic features despite their global distribution and several decades of focused research. Some of the uncertainties generated by difficulties in comparing Proterozoic and Phanerozoic terrains with adequate geodynamic constraints to Archean settings. However, some analogous geological settings from the Proterozoic and Phanerozoic were potentially overlooked and or understudied, thus limiting our understanding of Archean crustal evolution. For example, a Mesoproterozoic analog is the marble-rich domain, which is part of the central metasedimentary belt in the southwest Grenville province. Key geological characteristics are shared by Archean granite-greenstone terranes and the Mesoproterozoic analog. The comparison challenges the concept that Archean granite-greenstone terranes lack robust Proterozoic and Phanerozoic analogs. And the aim is to demonstrate their similarities and provide insights into Archean geodynamic settings. So a fundamental characteristic of Archean granite-greenstone terrains are the elongate septa of volcano sedimentary rocks that form keels within surrounding granitoid gneiss domes. The volcano sedimentary sequences are described as greenstone belts, which are often host to economic deposits. Greenstone belts are subdivided into two geochemical types, komatiite tholite and bimodal volcanic sequences. The volcanic and sedimentary components of greenstone belts vary significantly in type and volume between cratons. So the volcanic sequences and TTG granitoids in granite-greenstone terranes are compositionally bimodal and provide a fairly distinct geochemical fingerprint, despite occasionally being confused with island arcs. Although komatiites displaying spinifex textures are mostly restricted to the Archean, an adequate Proterozoic to Phanerozoic analog for Archean granite-greenstone terranes, like the marble-rich domain, should have similar but limited quantities of high-temperature mafic ultramafic magmatism. It is also important to recognize that only a limited volume of komatiites actually exist in greenstone sequences across granitoid-dominated areas such as the Superior, Slave, Pilbara, Cabval, amongst others. So in addition to bimodality, mafic to intermediate volcanic rocks display non-unique geochemical trends interpreted as crustal contamination, plume, and/or fluid flux signatures, often shown using the thorium-ytterbium versus niobium-ytterbium variation diagram. In this diagram, subduction-modified mantle sources trend in a broad field above and parallel to the modern mantle array. In contrast, variable assimilation of crust into mantle-derived magmas produces steep trends oblique to the mantle array, shown with the vectors. In the presence of synchronous crustal contamination, plume, and fluid flux magmatic signatures within individual greenstone sequences has resulted in contrasting interpretations regarding the presence or lack of subduction processes in the Archean. Similar to the volcanic rocks in greenstone belts, the enveloping granitoids also exhibit compositional diversity. Accordingly, Archean granitoids are classified into three main groups: TTG, potassic granite, and sanokitoid suites. The TTG and potassic granitoid suites can further be subdivided into high pressure, moderate pressure, and low pressure varieties, largely based on their strontium-yttrium ratios and niobium concentration. The potassic granitoids are generally inferred to result from partial melting and reworking of these TTG rocks. In contrast, the sanokitoid suite has compositions consistent with partial melting of metasomatically enriched lithospheric mantle. The compositional diversity of Archean TTG and Archean granitoids more generally betrays a duality in formation processes requiring uniformitarian-like and non-uniformitarian processes. So in addition to their complicated geochemical systematics, Archean granite-greenstone terranes often have a polyphase crustal formation and magmatic history. The polyphase crustal formation history generally involves one or more episodes of juvenile growth occurring in association with an older crustal substrate, which is broadly supported by the geochemistry of the volcanic rocks. Therefore, Archean granite-greenstone terranes often have discrete domains that are significantly older than the dominant age and isotope composition of magmatism in the terranes. Some examples of discrete older domains in largely juvenile Archean granite-greenstone terranes include a 3.29 billion-year-old xenocrust in the western Wabagoon terrane, and presence of reworked Mesoarchean sources, which Phil discussed. This makes discrimination of the east and west Wabagoon terranes using magmatic and crustal formation evidence more tenuous than previously recognized. In the Pilbara, there's generally a similar story of progressively younger episodes of crustal growth that occurred in association with an older crustal substrate. However, the earliest history of the Pilbara is still unclear because it's only represented by a few xenocrystic zircon grains at about 3.8 billion years. So now into the Proterozoic, where prior to the assembly of the supercontinent Rodinia, various tectonomagmatic events along the margin of Laurentia preceded terminal collision with Amazonia. The events are associated with tectonic processes including subduction failure, slab rollback, accretion, rifting, back arc extension, and/or plume impingement. These tectonomagmatic events influenced the local response of the Laurentian margin during orogenesis and the eventual geologic expression of the Grenville province. So one of these pre-Grenvillian tectonomagmatic events was the 1.3 to 1.2 billion year old formation of a bimodal plutonic volcanic magmatic belt accompanied with carbonate and siliciclastic dominated sedimentation, referred to as the central metasedimentary belt. The central metasedimentary belt has two distinct domains based on dominant sedimentary assemblage, which are the marble-rich and quartzite-rich domains. In contrast to the adjacent gneiss belt and quartzite-rich domain, the marble-rich domain reached lower metamorphic grades during orogenesis and preserves some primary igneous and sedimentary features, such as stromatolites. Not only does the marble-rich domain have comparable lithological and geochemical characteristics to Archean granite-greenstone terranes, but the TTG domes exhibit similar structural relationship with the surrounding volcanics. And just like the polyphase Archean TTG, the marble-rich domain has a polyphase crustal formation history with Mesoproterozoic TTG. So the comparison of Archean granite-greenstone terranes with the marble-rich domain demonstrates many shared characteristics, which I've documented here in this table. Hopefully you can read it, you might not be able to. The formation of the marble-rich domain is hypothetically related to back-arc rifting, as we originally interpreted it. And the similarities with Archean granite-greenstone terranes may suggest that, one, back-arc rifting is an analogous geodynamic setting to Archean granite-greenstone terrain formation. Two, instead of the abrupt onset of subduction processes, the formation of other analogous greenstone belts in the Proterozoic could be an indication of a gradual transition of geodynamic regimes rather than the abrupt onset of plate tectonics. And three, it is possible that the marble-rich domain and Archean granite-greenstone terranes form through an alternate geodynamic setting that has uniformitarian-like and non-uniformitarian characteristics, mimicking back-arc rifting. So these are some of the different hypothetical Archean geodynamic settings that you may be familiar with. Conceptually, I think it may be difficult to have a gradual shift from the drip or plume controlled tectonics into subduction settings, but a major question is, what does this transition look like? And I will say there's a recent geology article that was published in the last week looking at whether this is an abrupt or gradual transition, but I'm not going to get into that. So the gradual transition in the Proterozoic is actually also observed in metamorphic signatures, where we see the appearance of paired metamorphism in the Paleoproterozoic, which is clearly not as well established in the geologic record as the sustained paired metamorphism in the Phanerozoic. So using parameters representing the Archean environment on Earth and also those for Venus, numerical modeling has suggested that there would be a greater likelihood of lithospheric delamination. This tectonic process has been termed peel-back tectonics and is able to reconcile the lack of paired metamorphism in the Archean geologic record. These plots show the model output in fields and Archean metamorphism as points. And what these plots don't show is that there is actually a high pressure, lower temperature metamorphic imprint, but this becomes overprinted as the peel back continues. This is represented in Chowdhury's 2017 paper. Lithospheric peeling can also reconcile the formation of low, moderate, and high pressure TTG, regardless of the preferred composition of basaltic rocks. So this plot shows the PT conditions of melting and the composition of the basaltic source rocks. So the seismic structure of the crust and the structure of the subcontinental lithospheric mantle for the largest Archean provinces may also be conceptualized within the framework of lithospheric peeling. This includes the Slave, the Yilgarn, Capvel, and Superior. And I've just shown the geophysical representation of the Superior from about a decade ago. Some things have changed, but it's still is good to review. So the evidence suggests that the evolution of tectonic modes throughout Earth's history can be correlated with changes to orogenic style. It also implies that the transition between phases was rather diffuse or staggered instead of abrupt. And this fits in with the geochemical changes seen in volcanic rocks from crustal growth settings. Again, we see a similar transitional phase during the Proterozoic where lithospheric delamination potentially had a progressively more limited influence rather than the subduction of oceanic lithosphere. So this may also help to explain how a granite-greenstone terrane formed in the Mesoproterozoic. Peelback tectonics can also help to explain the large estimates of crustal destruction during the Archean. So in terms of potential implications for processes that govern differential metal endowment, variability in the efficiency of lithospheric delamination and geographic extent of the delamination would have significant control over the development of different deposit types and pathways. For example, total delamination may result in the formation of a vast juvenile terrane like the Abitibi, whereas incomplete delamination or multiple episodes of delamination may result in the formation of discrete juvenile terranes like the Wabigoon or the large but variable North Caribou terrane, respectively. Based on the described processes associated with peelback tectonics, drastic modifications are not required to our understanding of many ore deposit environments, and you can see that in the bottom right image. So in conclusion, peelback tectonics likely influenced Precambrian crustal growth and destruction. Peelback tectonics provides an additional mechanism to test against our geologic observations in the Archean. Peelback tectonics can reconcile many problems, such as the lack of paired metamorphism, coeval plume and fluid flux magmatic components in greenstone belts, the geochemical composition of low, moderate, high pressure TTG, the presence of convergent and extensional deformation, coeval crustal growth and reworking, the dome and keel structure of granite-greenstone terranes, etc. The transition of dominant tectonic mode through time was controlled by Earth's thermal evolution. And finally, no drastic modifications to our current understanding of Archean ore deposit formation are really required. However, a better understanding of lithospheric delamination may provide unforeseen advantages for future exploration. So thanks. I hope this highlighted some current developments in Archean geodynamics. And one thing I will say before I take any questions is I'm not saying every granite-greenstone terrane is formed through lithospheric peeling alone, but I'm trying to introduce the topic to the group so that you're aware of some of these current developments. Thank you.